Hello, it's me again. Now we're on 10I, relationship between speed, frequency, and wavelength. Carlos has a guitar, an instrument with strings of specific tension and length. So true. He plucks a string, which causes a fundamental standing wave of initial frequency F, and the wave speed forming the string. He then turns a knob to tighten the string without changing its length. When Carlo plucks the string again, the fundamental standing wave has a final frequency F, wavelength, and a wave speed. Mark each. Let's just do it here. All right. Let's just purposely take Mr. Burkhart's guitar out of tune. So here we go. I'm on capo 2, but that doesn't really matter. Oh yeah, it does. I'll be able to tighten the string. Right? So that's the. So what's going to happen to the pitch if I tighten it? It's getting higher. Did you hear that? It's all out of tune. All right, the pitch is higher when I tightened it. So X is next to higher pitch. The speed is going to be greater. So when it's a tighter string, right, it's easier for the wave to move through a tight string. And so it's going to move faster. And the wavelength is going to be equal to the wavelength. Why is the wavelength equal? Well, because the speed increased and the frequency increased, and those both increased, and the wavelength will stay the same. And let's see, why is the wavelength of the fundamental harmonic depends on the boundary? Oh, right, because this guitar is bound on both ends. I'm sorry, this guitar here, right? It's tied on both ends, and so you can only have so many nodes and antinodes with this open string. And if I wanted to change it, then I could put. Now I'm in the second capo. Now I've got a different string. Basically, I've changed the string length, and I've got a different note. And then I could go to fret 4. All right, and changing the length of the string. Then will also change. That will change the wavelength. But if you don't change the length of the string, then you can't change the wavelength of the string. Remember, the length is equal to a multiple of the wavelength. And so since that's, I don't know, it's bound on both ends, it's probably got some sort of condition. Maybe it's wavelength over 2, I'm not sure. All right, Dominique plays a trombone. Well, I don't have a trombone. I did in middle school, junior high, a long time ago. So I remember how it works. I liked playing the trombone. I wish I would have kept that up. When she plays the trombone, it causes a fundamental standing wave of initial frequency F, and then she goes the trombone goes longer, right? So what's happening is the speed is the same because it's the speed of sound in air. It's the sound is traveling through air. We're not changing the air. We're changing the length of the trombone. So as the trombone gets longer, it's got a longer wavelength because the wavelength is related to the length of whatever is making the sound. So a longer wavelength, a bigger wavelength means a smaller frequency, a lower frequency. It's a bigger. That's what I remember about trombones. All right, Angela, speaker to play a single note underwater. Ooh, special speaker that's not going to get ruined. Nice. So the sound is going to leave the water and enter the air. So what I know about solids, liquids, and gases is that sound travels faster in solids, and then next fastest in liquids, and then slowest in sound, actually. That's the reality. It's the speed of sound in water is like 1,000 meters per second or such ballpark compared to 340 ballpark in air, and even faster than that in solids. And that's because the molecules are closer together. The molecules in solids are very close together, the atoms are, and so it's easy for the sound to jump, through that material with those atoms or molecules being packed close together. And water is more dense, and those molecules are closer together than air. Nothing's touching really. They just bounce into each other once in a while. So this sound is going to jump out of the water, and we're definitely going to slow down, right? And the frequency is going to stay the same because the frequency is created by the speaker. So the speaker is making a frequency, and we can't change what the speaker is doing just because the sound jumps out of the water. So if the speed slows down, then the wavelength will get bigger or smaller. I'm sorry. The speed and the wavelength will both track each other. Standing waves in tubes. Consider a pipe that's 3 meters long and a gas. The speed of sound is 360. I don't know. That could just be hot air, honestly. Determine the longest 3 wavelengths and lowest 3 frequencies that resonate in the standing in the pipe. Following 2 cases for each part. First, draw the standing wave and pipe and explain how wavelength frequency were found. So that's open on both ends. You're going to have an antinode on both ends and a node in the middle. So the length would be equal to 1/2 the wavelength, or 2 times the length would be the wavelength. And since we know that the speed is 360, how long was the pipe? 3 meters. So 2 times the length is equal to the wavelength. So 6 meters is the wavelength. So 360 divided by 6 would be the hertz, 60 hertz. The next harmonic, we're going to have 2 nodes in it, equally spaced apart. So remember, this is 1.5 wavelengths, is it? 1 wavelength. A full wavelength. Yeah, this is a full wavelength. So the wavelength is equal to 3. The length is equal to the wavelength. It's 3 meters. So 360 divided by 3 is 120. And now we have to have 3 nodes inside the pipe for the next resonance. And so this would be 1.5, 3 1.5s, or 3 halves wavelengths. 3 halves of a full wavelength. So we can then, wavelength is 1.5. You divide 360 by 1.5. Is 180. So 360 divided by 1/2 is 180, huh? I don't think so. I think their logic is following, and then I don't think they did the math right at the end. Maybe they did. Oh my God. Because it's 3 halves wavelength equals length. The length is equal to 3 halves the wavelength. 2 halves, 1/2, 2 halves, 3 halves. So 2/3 the length is equal to the wavelength. So 2 times 3 equals, divided by 3 equals 2. 360 divided by 2 is 180. Okay, so what's wrong is the statement that wavelength is 1.5. It should be wavelength equals 2 meters, not 1.5 meters. So you've done it again, you incorrigible rat people. You can just repeat the process with the closed pipe. And we have a boundary condition where we have an antinode at the open end, and we have a node, a place of no vibration at the closed end. So the length of the pipe is equal to 1/4 wavelength for the lowest frequency right there. And so that means 4 times the length is equal to the wavelength. So 4 times 3 is 12. So 360 divided by 12, I hope, is 30. So there's the 12 right there. So now we have 3/4 of a wavelength. L is equal to 3/4 of a wavelength for the next one. So 4/3 the length is equal to the wavelength. So 4/3 times 3 is equal to 4 meters. And they got it right. 360 divided by 4 is 90. And now it's 5/4 because it always goes 1/4, 3/4, 5/4. So 4/5 of the length is equal to the wavelength. So 4/5 of 3 is 4 times 3 is 12 divided by 5. I have no idea. 12 is 2.4. They didn't write it out, but let's say 12 divided by 5 is 2.4. And if you do 360 divided by 2.4, hopefully you get 150 hertz. Well, at least they did the math right on this one. On part C, on the number line below, draw an open circle at each open pipe frequency you found in part A, and then use a pattern to get 3 more open pipe frequencies, and draw a closed circle at each closed pipe frequency, and use a pattern to get 3 more. So let's see, for our open pipe, we had 60, 120, 180. So there's an open at 60 right here, and 120 is right here, and 180 is right here. So what's the pattern? It goes every 60, right? So 180 plus 60 would be 240, 300, 360. The closed pipe is 30, 90, 150. So we go 30, 90, 150. It looks like they're happening every 60 hertz again. So 150 would be 210, 270, 330. That's the last one that fits. And I'm just going to stop right there because I'm not even sure we're going all the way to K this week.